diagonalization of a matrix. So when the matrix is diagonalized means it will be having its eigenvalues on the diagonal, on its diagonal or on its main diagonal axis. So to study this diagonalization, we need to study this theorem. So the theorem is, suppose the n by n matrix A. So A can be any matrix of order n into n. So it may be 2 into 2 or 3 into 3 or whatever. A is having linearly independent eigenvectors. So the eigenvectors of this A are independent. Then if these eigenvectors are the columns of a matrix S, if these are the columns of matrix X of this S, so to understand this one, instead of just going for a theory, let's see this one. Now A is this matrix. Yesterday we have found the eigenvalues and eigenvectors of this. A is this matrix which is of 2 into 2 order. Then it has 2 eigenvalues we know, and it has the eigenvectors also. So these 2 eigenvectors are independent. So the meaning is, if there is a matrix S, if there is a matrix S which is having these eigenvectors as its columns, means our S is having the eigenvector x1 as one of its columns and x2. How many are there? Those many have to be the columns. Now here only 2 eigenvectors are there, eigenvalues, so 5, 2. Then the thing says that if these 2 are linearly independent, and if S is the matrix of this, S is a matrix wherein the eigenvectors are the columns, then S inverse A into S is a diagonal matrix which is represented by a del kind of a thing. The eigenvalues of this A are the diagonals of this, let's call it as a del. The meaning is, this matrix, this S, how it is formed we have understood. If we have A S or S inverse A into S, then it is a matrix which will be having the eigenvalues on its diagonal. So the proof of this one is going in this fashion. So this is the statement of this theorem, the important one, and the proof of this one goes in this fashion. Now put eigenvectors xi in the columns of S as we have done here. So let's put it here. Once we do it, then compute A into S. So we go for calculating A into S. So if we go for calculating A into S, our A S is, let's do it with a different color. When A and S are multiplied, A into S, where these are the eigenvectors, then we get a matrix which will be lambda 1 into x1, lambda 2 into x2, and so on. If it is of nth order, then lambda n into xn, because we'll be having n number of eigenvalues as well as n number of eigenvectors. So it would be in this fashion. So just see it here. If it is A into S for this matrix, then it would be -1, -1, and 10 and 4. So which clearly says that. So it can be written as it is. So x1 lambda 1 we get, as we know, x1 is r1 1 and lambda 1 is -1. So it is nothing but lambda 1 times, it is nothing but lambda 1 is -1 times the x1. So we can write this one as lambda 1 into x1 it is. And the second one is lambda 2 into x2. Lambda 2 into x2, because lambda 1 is as minus 1 and this minus 1 is multiplied by this 1 1. So we are getting this is minus 1 and this lambda 2 is 2 and that 2 is multiplying this 5 and 2. So 5 and 2 is, so let's write this one as 2 into 5 and 2. So I hope this thing is clear, that when we multiply a into s, we are getting lambda 1 x1, lambda 2 x2 and so on. Then we can split this lambda 1 x1 as this same matrix can be written as x1 and lambda 1. So we can write this one as the product of the x1, x2, x3, the eigenvectors, and lambda 1, lambda 2, lambda 3 and so on. So it is nothing but x1, x2, x3 and so on up till xn and lambda 1, lambda 2 and all. When we multiply this, x1 will be multiplied with y1 and these all elements would be 0, and x2 except this all these elements would be 0. So in this fashion we can understand this. So it is as good as writing this minus 1, 10, 4 as lambda 1 x1, and which is nothing but, as we have seen, it is x1, x2, x3 and so on up till xn2 multiplied by lambda 1, lambda 2 and so on as shown here. So it is equal to this thing. Now when we go for finding, so this is the proof, and S inverse A, S inverse A, yes, is equal to this del matrix which is having lambda 1, lambda 2 on its diagonal. Let's prove that one also to understand this one and to complete this proof. S inverse A, S. So S inverse, what is our S? S is this matrix. So we find the inverse of this S. So S inverse is 1 and 2. We exchange, so this becomes 2 and 1, and we change the signs of this. So it is minus 5 and minus 1. And the value of this determinant, the value of this matrix is, the value of this determinant is 2 minus 5. So 1 into 2 minus 5 into 1. So divided by minus 3. So this is our S inverse. Then what is AS? Our AS is, let's write AS. Our AS is, already we have multiplied and obtained this matrix. This is our AS. So it is minus 1, 10 and minus 1, 4. And when we multiply this, when we are multiplying this, we are getting, so this is equal to, so 2 into minus 1, minus 2 by 3, and again this is minus into this, so minus plus 5 by 3 divided by minus 3 will make it as 3 by minus 3 by, 3 by minus 3, which will make it as 1. Similarly, so which is minus 1, 0, 0, 2, which are nothing but the eigenvalues of our matrix. So which can be written as, which is nothing but lambda 1, 0, 0, lambda 2, or just lambdas. By default these would be 2's. It is understood, and this matrix we are referring it by del. Such kind of a notation we use to refer it It is S inverse A into S. So which will be a diagonal element. Means to diagonalize, what we have to do is we have to find the eigenvalues, then eigenvectors, then let's form a matrix of eigenvectors and find its inverse also. Multiply A with this S and even this S inverse. So S inverse A into S, when we find, then the matrix will be the diagonalized one. And here A into S is always equal to S into this del. And in this we should remember that before this del, S has to be written, the multiplication A S we write and yes the del. Otherwise here we are getting the columns on the diagonal elements we are getting. If we write this in a reverse order, then we may get the rows multiplied with this and the order will not be the correct one. Will have the lambda 1 lambda 2 on the rows. So if we want on the lambda 1 lambda 2 as at different columns at particular orders, then it has to be S into del, and certainly S inverse A into S is equal to this del, and even the A is equal to S and S del S inverse. So one can try that. The S matrix we know it is our S matrix. When S matrix del and when S matrix del and S inverse are multiplied, we are going to get A. So just the thing is reverse. To obtain this del, we are writing S inverse A into S. Now here we write S into del S inverse to obtain this A. A can be even obtained by multiplying S del S inverse. So here S inverse will come at last. So this is regarding that diagonalization. Here some things we need to know. So few of the remarks are, if matrix A has repeated eigenvalues, means if the values of lambda 1 lambda 2 are same, then n eigenvectors are automatically. If A has no repeated eigenvalues, then certainly it will have lambda 1 lambda 2 as different, and it will have different eigenvectors and it can be diagonalized, but the things may not be same if the roots are repeated. So in those cases we may not have the eigenvectors as independent, linearly independent, then the diagonalization may not be possible. Then the remark 2 is, the diagonalizing of matrix S is not unique. Even by multiplying by some scalar, multiply the columns of S by any non-zero constants also, one can go for diagonalization. It says that the order of the eigenvectors in S and eigenvalues in del is automatically the same. Then know all matrices possesses n linearly independent eigenvectors. Like not all matrices have n linearly independent eigenvectors. So not all matrices are diagonalizable. So few of the matrices will not have linearly independent eigenvectors. So they cannot be diagonalized. The standard example is this one. Let's see, here A is 0, 0 and 1, 0. And when we go for its solving, so minus lambda, A minus lambda I, when we apply, so lambda 1 as it is of order 2, lambda 1 is equal to lambda 2 is equal to 0. Since it is a triangular with zeros on the diagonal, so this will have lambda square, and the eigenvectors of this A are, we know how to find the eigenvectors of this. Now here 0, 1 and 0, 0 in this matrix, if we go for writing the values of 0 minus lambda, that is minus lambda, 1, 0 minus lambda, then lambdas are 0. So when we go for its solving, the eigenvector is a 0. So the S matrix cannot be constructed for such kind of things, such kind of matrices. Then let's see another example, repeated eigenvalues. If we consider this matrix, then here the eigenvalues are repeated for this 3, 1, 0, 3. If we go for solving like a minus lambda I is equal to 0, we get the roots as 3 and 3. And to find the eigenvectors, if we substitute 3 minus 3, it makes the first term becomes 0, this would be 1, this is as it is 0, and again 3 minus lambda will make it as 3 minus 3, 0. So we have again a similar kind of a situation wherein 0, 1, 0, 0 will be there, and for which we need to find the two unknowns. So the values again become the, like, we fail in finding the particular values of eigenvectors, and the same case is with this. So we come for the conclusion that diagonalizability of A depends on enough eigenvectors, and invertibility of A depends on non-zero eigenvalues. So certainly every matrix cannot be diagonalizable. It depends, the diagonalizability of A depends on its eigenvectors, whether they are present or no, the valid eigenvectors are existing or no, and invertibility depends on non-zero eigenvalues. Then the next point is regarding, so the conclusion is eigenvectors x1, x2 and so on up till xk corresponds to, if of a matrix eigenvectors x1, x2 up to xk corresponds to different eigenvalues lambda 1, lambda 2 and so on up till lambda k, then those eigenvectors are linearly independent. And if the eigenvectors are linearly independent, we can go for constructing a diagonal matrix. Then examples of diagonalization. So let's consider the main point of this section is S inverse AS is equal to, we need to write it as a del. The eigenmatrix S converts A into eigenvalue matrix, a diagonal. So let's see how does it happen. So projection of A is this 1 by 2, 1 by 2, 1 by 2 and 1 by 2. Has eigenvalue matrix as this way. The eigenvectors go into the columns of S. So we go for finding this example. Here the given S is this one, 1, 1, 1 minus 1. A is given and the eigenvalue matrix means the diagonalized matrix is given. Del is given to us. And we have to prove that AS is equal to S del or what? Our A, yes, A into yes. We can find A into yes. So this A into yes is, when we write A into yes, we are getting 1 by 2 plus 1 by 2, which is 1. Again 1 by 2 minus 1 by 2, which will be 0. Again this 1 by 2, 1 by 2, which will be 1, and 1 by 2 minus 1 by 2 as a 0. Let's see even the same we get or what after multiplying this yes and A. So yes is again this 1 and this del is this one. Let's see. So even multiplying yes and this del will give us the same result. Hence the conclusion is the last equation can be verified. So that is S inverse A yes is this del, or AS is equal to SA. When we take this yes on this side, it would be S inverse AS, which is equal to this del, the same. Then let's see another problem. the eigenvalues themselves are not so clear for a rotation. So let's learn with the rotation matrix, a 90-degree rotation matrix. We know that when identity matrix of order 2 into 2 is like 1 0 and 0 1. So the first vector of that one was 1 0, and when it is 90-degree rotated it turns to be 0 1, and when 0 1 is rotated by 90 degrees it goes to minus 1 0. Then let's find what are the eigenvalues of that rotated matrix by 90 degrees. So certainly when we write A minus lambda I, so here lambdas would come, and A minus lambda I, so it would be 0 minus lambda, 0 minus lambda. When we go for finding its eigenvalues, it would be lambda square plus 1. Hence our roots would be plus or minus root of minus 1. So root of minus 1 is plus or minus I. So let's say lambda 1 is plus I, lambda 2 is minus I. So the eigenvectors are also not real, as the eigenvalues are also not real. So as eigenvalues are imaginary, eigenvectors too will be imaginary. Let's see what it would be. So when we write k minus lambda I, so it would be a minus lambda I x1. So for the root x1, when we substitute the first root, so it would be minus I, a minus lambda I, a is 0. But K matrix we write because it is a rotated matrix. So K minus lambda I would give the null matrix. The values of y and z would be 1 minus I. And for when we substitute lambda 2, that is minus I here, we get plus i's, and 1 minus 1. So when we solve for y and z, but for a null matrix, for a null solution, we get x2 is equal to 1i. So our S matrix would be 1 minus I and 1 plus I, and S inverse Ks is equal to this much. So this shows that the complex numbers are needed even for real matrices. So let's see how to find the powers and products. So that how can we find ak and a to the power k and a into p. So the eigenvalue of a square are exactly lambda 1 square lambda 2. Means if we say A is our matrix, and if eigenvalues of A are lambda 1, lambda 2, lambda 3, etc. Let's think that A is some matrix having some values, and lambda 1 and lambda 2 are its, let's say it is 2 into 2 order, lambda 1 and lambda 2 are its eigenvalues. Then the thing says that A square, then A square matrix will be having the lambda 1 square and lambda 2 square as its eigenvalues. So the statement says that if the eigenvalues of A square are lambda 1 square, lambda 2 square, how many as the order of Ra? And every eigenvector of A is also eigenvector of A square. We start from Ax is equal to lambda x. This is our main equation, Ax is equal to lambda x for solvability, and multiply again by A. So this Ax, we multiply Ax is equal to lambda x equation we take and multiply on either side by A. So we get A square x is equal to A into lambda x. So that is equal to, so this we write lambda is a constant, let's take it outside. So lambda A into x we write is equal to, now what is Ax? Ax is equal to lambda x. When we substitute we get lambda square x. So this shows that the eigenvectors of A square are lambda 1 square, lambda 2 square, and so on. And the eigenvalues are lambda 1 square and all, and eigenvectors are the same. The eigenvectors of A are even the eigenvectors of A square also. Now the question is how to find the eigenvalues of A square. We know how to find the eigenvalues of A, then how about A square? So to find the eigenvalues of A square, so S inverse A into S is equal to A. We know S inverse A into S is equal to A. So we multiply S inverse A into S another time to get this del square. So this will be, we know that we get the eigenvalues on the diagonal of this del of this A matrix when we have S inverse A into S. Hence, if we know the eigenvalues of this A and eigenvectors of this A, then we know how to construct S. And as S is there, S inverse also. And we have the diagonal matrix, that is del. If we know these all, then our A square, the eigenvalues of A square would be like S inverse A square into S is equal to this del square. So simply we need to find what is A square, and to that A square multiply, find A square S and multiply that one by S inverse. Already S inverse and S are with us, just we need to go for finding yes A square. Then will get this del square. This del square will have the diagonal elements, and those are nothing but the eigenvalues of this A square. Similarly, if we are supposed to find the eigenvalues of A to the power k, then lambda 1 k, lambda 2 raised to k, and so on up till r. So these will be the eigenvalues of this A raised to k. Hence it may be A square. If we want the eigenvalues of A cube, then lambda 1 raised to 3, lambda 2 raised to 3, and so on. And each eigenvector of that A is still an eigenvector of AK, and we can go for this del k finding by multiplying S inverse A into S as many times as k. So S inverse A raised to k, yes it would be. So on this we can go for solving the problems. And another thing regarding diagonalizable thing is, so diagonalizable matrices share the same eigenvector matrix, yes, if and only if AB is equal to BA. We know that AB is not equal to BA usually, and if AB is equal to BA has to happen, then the eigenvector matrix, yes, should be same for both these A and B's. So the proof of that one is AB is equal to BA, A is equal to, we know that it is yes, the del S inverse, and B is equal to yes, the del inverse, the del S inverse. And initially we think that these two are different, and we can multiply each other. So A into B is equal to yes, del 1 S inverse, and yes, del 2 S inverse. So this will be equal to yes, del 1 del 2 S inverse. And if BA, then we can write this, if BA we do, then same thing, del 2 and del 1 will come, the same equation. So this is equal to again yes, del 2 del 1 S inverse. So since if del 1 and del 2 is equal to del 2 and del 1, so diagonal matrices always commute this A into B is equal to B into A, and it is possible if the same eigenvectors are existing. So diagonalizable matrices share the same eigenvector matrix, yes, and if it is same, then AB is equal to BA. Let's solve the question paper problem, that is, factor the matrix A into A x inverse using diagonalization, and hence find A3. So let's solve this problem. So A minus lambda I is equal to, it is 1 minus lambda 2 0 3 minus lambda. So A minus lambda I is equal to 0. We need to solve. So let's find the equation corresponding to this one and get the eigenvalues. So when we solve it for the eigenvalues, we get lambda 1 is equal to 1 and lambda 2 is equal to 3. Then we need to find the eigenvectors corresponding to lambda 1 and lambda 2. So let's find that. So 1, let's do it with lambda 1 is equal to 1. So when we substitute, it becomes 1 here. It becomes 0, 2, 0, and 3 minus 1 is 2. Let's take yz as this unknowns. So is equal to a null space because it has to satisfy A minus lambda I is equal to 0. So when we solve this, to solve this equation, so we need to get the values of y and z other than this 0, 0. So let this z be, this y is equal to, let's say if y is equal to, now we have the equation as y, 0 into y plus 2z is equal to 0. The same equation repeats here. Now the solution of this implies z is equal to 0. But what should be the value of y? Y can be 0 or y can be 1, y can be 2, y can be 3. In this equation, if I write 0, 2 and 0, 2 multiplied by, if I write this as 1, 0, then also I'll get this equation as 0 into 1 as a 0 and 2 into z as 0. So as this term is 0, we can take up a 1, 2 and anything here, but all the other ones like 2, 3 and even the other ones 4 etc., they are the multiples of this one. So let's take the vector, the eigenvector for y1 for this lambda 1 is equal to 1 as, so let's take the vector, let's say rx1 is equal to 1, 0. Similarly for lambda 2 is equal to, let's go for finding for lambda 2 is equal to 3. When we substitute, then we get this A minus lambda I matrix as, this is 3. So it would be minus 2, 2, 0 and 3 minus 3 would be 0. Again the same complexity, that is, let's write y and z here and let's equalize the 2, 0, 0. And what can be the solutions? We get the equation for this one as minus 2y plus 2z is equal to 0. Then by looking at this 2 is the same, means the values of y and z have to be same, but they have to be, the value of this y, let's say if this is minus 2, then this is plus 2, it has to be. So 1 and 1, the values of y and z have to be same. So if we take them as 0 also, it satisfies. If we take 1 also, it satisfies. 2 also, it satisfies. But as 2, 3 and all are the linear multiples of 1, so let's take the x2, the eigenvector for lambda 2 is equal to x2 as 1, 1. Then our S matrix is the eigenvector matrix, so which will be given by the first vector, that is 1 0, and the second one 1 1. And S inverse, this S inverse is equal to, from the previous knowledge we know that we need to exchange the diagonal elements, but they are same, so no difference even after exchanging. And we need to change the sign of the minor diagonal elements, so let's make this one as 1, and this diagonal value is 1 into 1 minus 1 0, so which will be 1, so S inverse is this much. So let's find what is A. Then A is equal to, we know that it is yes the del, let's write in this way, and yes inverse, and in the problem yes is written as x, so S is equal to x. Our S is, let's write it here, our S is 1 0 1 1, so 1 0 1 1. Our this del is the diagonal matrix wherein the lambda 1 and lambda 2 lie on the diagonal, other elements are 0. Our diagonals, our eigenvalues are 1, so 1 0 it is, and the 0, the second diagonal element is 3. And S inverse is, it is a 1 minus 1 0 and 1. When we multiply these two, we are getting the result as, it is a 1 into 1, and 1 into 0 is 0, and 1 into 1, this 1 into 0 is 0, so we get, so 1 into 0, 1 into 3, we get 3 here, and 1 into 0, 0, we get 0 here, and then 1 to 0, this we get as 3. So this 2 when they are multiplied. So let's again multiply this result with this matrix. So it is 1 minus 1 0 and 1, so which is equal to, so when we multiply these two, 1 into 1, it is 1, and 3 into 0 0, and 1 and 2 minus 1, it is minus 1, and 3 into 1, it is 2, 0 into 3 means 0 1, it is 0, 3 into 0, it is 0, so we get this as a 0, and this 0 into this minus 1 is 0, but 3 into 1 is 3. So our A is nothing but yes, the diagonal element, the diagonal matrix, yes inverse. So this has been proved. We are supposed to find A cube, and from this del raised to k is nothing but S inverse A into yes those many times, that is yes inverse A raised to k yes. And A cube is, to find A cube, let's write A cube. A cube is equal to, A cube is the 3 times multiplication of this A, 3 times multiplication of A, so it is nothing but A into A square. So we need to first find A square and then again multiply it by this. So let's find A square. A square is equal to A into A. A into A. So let's find. So when we multiply this, we get it as, one can check, it was 1 So 1 into 1, it is 1, and this is 2 into 0, and 3 into 1 into 0, 2 into 3, this is a 6 plus. So we get, apply these two matrices, we get 1, 8, 0, 9. One can check this. Then a cube is equal to a into this. So let's write a, that is 1, 2, 0, 3 multiplied with this a square. A square is 1, 8, 0, 9. When we multiply these two, we get that it is again 1 into 1 and 2 into 0, it is 1, and 1 into 8 and 2 into 9. So 18 plus 8, 26. 1 into 1 and 3 into 0, again this 0 into 1 and 3 into 0, 0, and this works out to be 0 into 8, 3 into 9, 27. So this is our A3. Then let's check one of the property. We have seen that if we find a cube, then the eigenvalues of this one would be lambda 1 would be, the eigenvalues of this A3 have to be, like our lambda 1 is 1, it should be lambda 1 of this one has to be, the A cube's eigenvectors are the lambda 1 cube and lambda 2 cube, they have to be. Let's check whether the eigenvalues of this A3 are, let's say, lambda 1 dash, and whether this lambda 1 dash is equal to lambda 1 the cube or what. Yes. And even lambda 2 dash, the A cube's eigenvector second, whether it is 3 times, it is, whether it is equal to lambda 2 raised to 3 or not. So when we solve this, we are getting, let's find a minus lambda I. When we solve like that, so for this we get 1 minus lambda 1 dash, and this is 27 minus lambda 2 dash is equal to 0, and certainly lambda 1 dash is equal to, lambda 1 dash is equal to 1, and which we can write it as 1 raised to 3. It is, of course, the thing is lambda 1 dash is lambda 1 to the power 3, that is true, and lambda 2 is equal to, lambda 2 dash is equal to 27, and which is equal to, lambda 2 is 3, so it is 3 to the power 3, which is equal to lambda 2 to the power 3. So we have understood how to find this a cube and all.